So we have this cylindrical coordinate system, and why should we even care about it? What is it useful for? And so one thing is that cylindrical coordinates are especially convenient for representing cylinders. The name is kind of fitting, right? They don't choose the name out of thin air. Cylindrical coordinates make you think of cylinders, and that's exactly why we have them. Is it helps us, it makes it especially nice when we're looking at cylinders. So for example, let's take a right circular cylinder. So x squared plus y squared is 9. That's a right circular cylinder that goes up the z-axis. So I'm going to just kind of sketch it roughly here. Here's the cylinder. And if I convert this to cylindrical coordinates, this equation, well, x squared plus y squared, that's the same thing as r squared. So this would say r squared equals 9. Or another way you could state this, if you take the square root, r would be plus or minus 3, but here you would just go with r equals 3. Let's look at another cylinder equation, maybe not a right circular one. Let's go with x squared plus y squared equals 4z. So this is if I graph this, it would go upwards on the z-axis, and this is a paraboloid. And again, we can convert this equation. If I plug in for x squared plus y squared, it would be r squared equals 4z. And then you take the square root. Again, here you don't have to worry about plus or minus. R would be 2 times the square root of z. And then the last one, let's look at the equation of a cone. So x squared plus y squared equals z squared. So if I look at the graph here, it would go up and down the z-axis. Here's my cone I got going on. And if I convert this to cylindrical coordinates, this equation, it would be r squared equals z squared. And you take the square root. Again, you don't have to worry about plus or minus with r. R will be equal to z. So it's nice if you look at all these equations now, they're much nicer than the equations we started with. They're more simplified, they're easier to handle, and so cylindrical coordinates is very nice for these kinds of shapes, these surfaces. So let's do a little bit more where we're converting some equations. So let's find an equation in cylindrical coordinates for the surface represented by each rectangular equation. So those would be, let's look at our first one, x squared plus y squared equals 4z squared. If you look up what kind of surface this is in that table, this is an elliptic tone. So we're swapping out here for x squared plus y squared. You're going to replace that with r squared equals 4z squared. So you could leave the equation like this, or you could, so because z is being squared here, I think we're going to leave the equation like this here. Yep. Once you get rid of x and y, you've converted the equation to cylindrical. So now for the next one, let's convert y squared equals x. And this surface, it's a parabolic cylinder, in case you were interested. And now we're going to plug in our formula. So y is r sine theta, so it'll be r sine theta squared, and x is r cosine theta. So now I'm going to square the left side. R squared sine squared equals r cosine theta, and move everything to one side. So move everything over to the left, r cosine theta 0. And we're going to factor out an r. And then you can divide by r here to get r sine squared theta minus cosine theta equals 0. And then solve for r now. R sine squared theta equals cosine theta. R is cosine theta over sine squared theta. So you could leave it like that, or you can rewrite this as cosecant theta cotangent theta. And again here I don't have x's and y's, and my equation says r equals, so I'm done converting this equation.